Hello engineers, welcome to the new video of the course, and in this particular video we are going to simulate one circuit, that is a logarithmic circuit, which we had seen in the previous session. So if you could remember, in the previous session we had seen this particular circuit theoretically, and we had deduced the formula for it. That is, this was the formula, and in this particular formula we can clearly see that the output voltage is directly proportional to the natural log of my input signal, right? So whatever the input signal might be, so at the output side I should get the log of my input signal, right? So this is what we saw in the previous session. So this was the actual formula, where Vt was my thermal voltage, this was my reverse saturation current, and Rin it is the resistor, okay, that was present at the input side. So Vt, Is and Rin, these three parameters, if I fix them, so I can actually play with my input and output signal, right? Okay, great. So now let's look upon the practical scenario. That means we are going to simulate this particular circuit onto the LTspice software, and we will check if we are getting the log of my input signal or not. Okay, great. So for that you just need to focus upon this particular circuit. I'm going to provide this particular input voltage, that is a kind of a ramp signal. That means it starts from 0 volts to 5 volts for around 1 millisecond. So it should look something like this. So you see, it is starting from 0 volts and obviously it is starting from 0 seconds, and till 1 millisecond it will rise up till 5 volts. Okay, so at 5 volts I'm getting at 1 millisecond I'm getting 5 volts of signal, right? Something like this, a kind of ramp signal, a kind of triangular like shape. If I try to jot down this particular point up to 1 millivolt, so what I can say is that it is a kind of a triangular in shape. Okay, but you see it's a kind of a ramp signal, right? A straight line passing through an origin. Okay, if you are a mathematical student, so you can say that a straight line that is passing from an origin. Okay, great. Now, so you see over here, this is my logarithmic circuit, wherein my Rin is 1 kilo ohm, and this is the diode that I'm going to use, that is 1N4148. okay, and at the output side I should expect this kind of graph. Okay, now why I should expect this kind of graph? Is there any logic behind it? Yes, there is one logic behind it. What I'll suggest to you all guys is that I'll just pin this particular link into the resources section, and I'll also give this particular link in the description box, as I'm going to upload this particular video on my YouTube channel. So you just come down, and over here yeah, you see this is a log amplifier. Just a second. Yeah, this is a log amplifier, and this is the equation which we had got, and over here this particular website has given the simulation result. Okay, you see they are providing input voltage which starts from 0 volts to 5 volts. This is a kind of a ramp signal, and then you see at the output side they are getting this kind of curve. Okay, so do we trust them? So should we trust them blindly? The reason is not. Why? Because you see the Opamp that they had mentioned over here, that is an ideal Opamp. Okay, and we should use practical Opamp. Okay, obviously we are not going to use an ideal case Opamp, okay, in our daily life, right? We are going to use one practical Opamp which has VCC and minus VCC, the supply voltages. Okay, so depending upon this particular website, we should expect this kind of output. Okay, this kind of output. So that's why if you see very clearly, if I'm providing this kind of input signal, so I should get this kind of result at the output side. Okay, great. Again, we should not trust them blindly. Let's do certain mathematical calculations. So for that I'm using one software, that is Desmos software, Desmos graphing calculator. So first thing first, we need to focus upon my input signal. So let me just write over here the input signal, that is y is equivalent to mx plus c. Okay, take m as 1 for time being and c as 0, so that will be y is equal to x, right? So y is what? Let's suppose for time being, if I consider y as my output signal, v out, which is equivalent to my x. Let's assume for time being it is my input signal, so v in, right? So you see v out is equal to v in, so you will get this kind of curve, something like this, a straight line passing through an origin, something like this, whose slope is almost constant, right? Whatever its slope might be, for time being we had assume it as 1. Just a second, let me erase this, it's not drawn in proper way. Yeah, something like this. Okay, whatever the slope might be, the slope is constant throughout, right? Okay, so now let me erase this, and let's see if we are getting the result or not. So I'll just write over here, just a second. Yeah, I'll just write over here y is equivalent to x. Yeah, you see I'm getting one line, a straight line passing through an origin. Okay, if you want, just take a screenshot of it. As I had mentioned over here, y is my output signal, x is my input signal. Alright, I believe that you might have taken a screenshot of it. Now let me go over here and you see I'm getting this kind of signal, or rather I'm giving this kind of signal to the input of this particular logarithmic amplifier. Great. Now just come over here and now let me just write another equation, that is y is equals to log of x. Okay, now why I'm writing this particular equation, because you see over here, this is what we want at the output side. My output signal should be proportional to the natural log of my input signal, right? So for that, let me just write over here y, that is my v out, is equivalent to log of x. Okay, so before that, let me just write it over here. Let me just mention over here, y is equivalent to log of x. Okay, that means my v out is equivalent to log of my v in, and we are not taking into account is, okay, r in and vt. Okay, we are not taking these three particular parameters into account as of now. We are not focusing on them. We are just focusing on this particular equation. Okay, we are just focusing upon this particular equation. Let's see what value we will get. So y is equals to log of x. Okay, so now let me put y is equivalent to log of x. Let me just put this particular value over here, log of x. Okay, so now you just have a look over here on this particular curve. You are getting a curve in such a way that it is starting from negative y-axis and it is going to positive y-axis, and then it is incrementing, right, as our x is increasing. Okay, now just by looking at this particular graph, you might say that whatever the curve that you had drawn onto the blackboard, that is wrong. Okay, but before that, it's my request to you that you just please take a screenshot of this particular equation and this particular graph. Alright, I believe that you might have taken a screenshot of it. So now let me go to the blackboard. Yeah, so now just by looking at this particular graph, just a second. Yeah, just by looking at this particular graph that we had obtained over here onto the calculator, graphing calculator, you might say that the graph that we had obtained over here, it is wrong. So our assumption is wrong. So my dear student, our assumption is not wrong. Just the thing is that we had written the equation in the improper way, because if you look very clearly, our equation is v out is equal to minus of log of v in, right? So over here there is one negative sign. Let me just put one negative sign. Okay, as we are dealing with the negative feedback, so there is one negative sign which we had not taken into account while writing the equation over here. So now let me just put the negative sign over here, and then you see the graph over here. Yeah, you see, the moment I put the negative sign in front of this log of x, so you see I'm getting this kind of curve which we were expecting, right? See, this kind of curve which we were expecting. Yeah, that's the different thing, that it is starting from positive y-axis and then it is going to the negative y-axis, right? Okay, so that is not the point of our interest. Our interest is to obtain this kind of curve, right? And if you look over here onto this particular website, even they are mentioning that they got this kind of curve at the output side of this particular circuit, right? Getting my point? Okay, if you want, you just refer this particular website. Okay, actually they were talking about diodes throughout this particular website, but yeah, this is the good point which they had mentioned over here. Okay, great. So now let's do it practically. Okay, let's see if we are able to obtain same kind of curve or not with the help of a practical op amp. So I'm going onto the LTspice software, and you just look over here. This is the circuit that I had designed. I had taken supply voltages as plus 15, minus 15. The op amp that I had used, it is LM741. Obviously in this entire course we are dealing with this particular op amp only. The diode that I had used, that is IN4148. This is my resistor Rin, which is of 1 kilo ohm. And this is my transient analysis. So I'm analyzing it from 0 second to 1 millisecond. And let me just show you the pulse, that how exactly you are going to give the pulse waveform, or basically the ramp waveform. Okay, so just need to click over here onto the pulse, and these are the settings that you need to focus upon. So obviously my initial voltage should be 0 volts. Let me go onto the blackboard. Yeah, the initial voltage is 0 volts. Let me just use some different color. Yeah, the initial voltage is of 0 volts. Okay, great. So this is what it is mentioned over here. Then V on time, V on the final voltage should be 5 volts. So yeah, this is what I can say. Final voltage is of 5 volts. So my signal should move from 0 volts to 5 volts. Okay, 0 volts to 5 volts. Okay, getting my point? Then the next point is T delay. Obviously we don't want any delay. So let's suppose if I'm giving a delay of, let's suppose if T delay, if I had entered the value as 1 millisecond. So what does that mean? That means, see, from 0 millisecond to 1 millisecond, maybe to 1 millisecond, there won't be any signal, right? Okay, this is my y-axis, that is my v in. Okay, from 0 to 1 millisecond there won't be any signal, provided if I'm giving t delay as 1 millisecond, but after that I will get this kind of signal. So you know, the signal which is appearing over here at 0 millisecond, it will start appearing at 1 millisecond, and at around 2 millisecond I will get this kind of signal, okay, which we are getting at 1 millisecond. Okay, something like this. So this will be my 2 millisecond, and this will be my 5 volts. Okay, 5 volts. Okay, so you see we are getting a delay of 1 millisecond if I enter this particular value. Okay, you just try to do it on your own. Okay, but as of now I don't want any delay, so I just put in the value as 0, and t rise time, obviously it should be of 1 millisecond, so till 1 millisecond it should rise. Okay, you just have a look over here, till 1 millisecond it should rise, and t fall should be 0. Okay, the moment it the moment it arrives at this particular point at 1 millisecond, that is of 5 volts, it should fall very quickly. Okay, it should fall very quickly, whereas the rise time is of around 1 millisecond. Okay, getting my point? Okay, so t, and then there is one t on time, that should also be a 0 second. Obviously we don't want any on time. Okay, and then period is of 1 millisecond. That means it is talking about the frequency, as frequency is 1 by time period, that is 1 by 1 millisecond, that is around 1 kilohertz, right? Okay, and then we just want to see it for 1 cycle, so I had entered it as 1. Okay, getting my point? I hope that you understood that why exactly we had entered these values for these respective parameters. Okay, great. Just click on OK, and then I'll just run this particular circuit, and then I'll just make two planes, and over here onto this particular part I'll just plot my input signal. Yeah, you see my input signal, it is starting from 0 volts and it is ending at 5 volts. You just have a look over here. This is my ramp signal. If at all it is not visible to you all guys, let me just plot it for you. Just a second. I'm not so good in drawing, so let me draw it one more time. Just a second. Yeah, so you just have a look over here at this particular signal. Yeah, so this particular point is 5 volts and it is starting from 0 volts, and you just have a look over here. Just a second. Yeah, 1 millisecond. So our time period, it is from 0 millisecond to 1 millisecond. So this particular point, it is 0 millisecond and 0 volts, and this particular point is 1 millisecond and it is 5 volts. 5 volts. Getting my point? Great. I hope that you understood that how exactly we plotted this particular waveform. Now we need to focus upon the output waveform. So let's see what kind of output waveform that we will get over here. So I'll just click over here onto this plane, and then I'll just put my pen over here, and you just have a look over here the kind of waveform that we are getting. Let me change the color if at all this particular part is not visible to you, and let me just zoom out this particular waveform for you all guys. Yeah, you just have a look over here. We were expecting this kind of curve. Where it is? Just a second. Yeah, we were actually expecting this kind of curve at the output side. See, just a second. Yeah, we were actually expecting this kind of curve at the output side. Also, when we plotted this particular waveform onto that particular graphing calculator, we were supposed to get this kind of curve, right? But we are not getting this kind of curve. So what can be the reason behind that? What can be the reason behind that? So it's my request to you all guys that you please pause this particular video over here and please try to think in your mind. Alright, I believe that you might have tried your best to think upon the solution, but let me just give you the answer. You just have a look over here. Just by looking at this particular waveform, what we can conclude is that the Opamp that we are using, it is unstable. That is LM741. For this particular application, that is for logarithmic application, the Opamp that we are using, it is highly unstable. Okay. So now what we will do, it's my request to you, if at all you are just watching this particular graph, please take a screenshot of it and save it as maybe LM741. Okay, because this particular output waveform that we had obtained, it is for LM741. If you want, I'll just mark over here. I'll just highlight it. So this particular waveform that we had got, it is for LM741. Okay. Okay, great. I hope that you might have taken a screenshot of it. Now let me erase it and let me go back, and now instead of LM741, now let me delete it and let me use some another Opamp which is quite stable as compared to this particular op amp that was LM741. So instead of LM741, maybe I will go with OP07, which is quite stable as compared to this particular op amp. So now let me put it over here. Let me connect it onto this particular circuit, and now let me run it. Alright, so you just have a look over here. See what kind of waveform that we are getting over here. Just have a look over here. What kind of waveform that we are getting. If at all it is not visible to you, I'll just mark it for you all guys. See, something like this. Okay, something like this. So this particular plot is for OP07. Again, it's my request to you. Please take a screenshot of it. This is 0, by the way. This is OP07. Okay. Alright, I believe that you might have taken a screenshot of it. Okay. Now, if you could remember, forget about the values that are present over here. For a second, just forget about it. In case of LM741, we were getting this kind of waveform, something like this. Okay. It was something like this, and then after some point, it was constant. Okay. Over there, if you check, it was 0 volts over here. Okay. That's why I said for a time being, just forget about this particular value. Okay. But now, if you look upon this particular curve, this was for LM741. Okay. And this is for OP07. So that means what? OP07, it is more stable as compared to Opamp LM741. Okay, less stable as compared to it, And when we see this, that is OP071, which is more stable as compared to LM741, what we can say is that this particular curve that we had obtained with this particular op amp, that is OP071, it is quite closer to a logarithmic curve. Okay, quite closer to logarithmic curve. That means it's my request to you, just take a screenshot of it. Alright, I believe that you might have taken a screenshot of it. Now let me go to the blackboard. Yeah, that means this particular curve that we were expecting, it is quite closer to it. You just have a look over here. It is quite closer to it. Not exactly similar, but still it is quite closer to it. Also, if you look at the values over here, it is somewhat similar to the this particular op amp which we saw over here onto this particular website, that is minus 460 millivolts to minus 600 millivolt. Although over here, I think it is starting from 0 millivolts and it is going up till 500 or I guess 600 millivolts. Okay, quite closer to it, but it is not similar. Okay, that is fine. Okay, that is also fine. Now, instead of OP071, I will use more stable op amp. Let's suppose AD8030. So now instead of using OP07, I will switch to AD8030. Let me move over here. Yeah, see this particular op amp, AD8030. Click on OK. Yeah. So now that I had connected this particular op amp and onto this particular circuit, so now let me just run this particular circuit and then just focus upon the graph that we might obtain over here. Okay, just focus upon the graph that we might obtain over here. Okay, so let me run. Where is that particular command? Yeah, over here, run. Yeah, now you just look upon this particular graph. Now you just have a look onto this particular graph. See, it is starting somewhere around 300 millivolts and it is going down, down, and then after some point it is almost constant. So now if you look very clearly, this particular curve, it is quite closer to a logarithmic curve. Now let me just highlight it for your understanding purpose. See, this particular curve, it is almost closer to a logarithmic curve. See, I hope this particular part is visible to you all guys. See, this particular curve, it is almost equivalent to a logarithmic curve, which we wanted, right? Okay. Also, if you see this particular values which is present on y-axis, it is quite closer to the values of the website that I am giving. Okay. Just try to check this particular values if you want. You can clearly see it is starting from around maybe 300 millivolts. Okay, and then it is going up till around 640 millivolts, and after that particular point it is almost constant, right? It is constant. Okay, so it's my request to you that you please take a screenshot of it. Alright, I believe that you might have taken a screenshot of it. So now let me erase it and let's go onto that particular website. Sorry. Yeah, let's go onto that particular website, and you see it is starting from around maybe 450 millivolts and it is going up till 646, 60 millivolts, and after that it might be constant or whatever that is, right? Although it shouldn't be constant because it is going down and down and down. That is a different thing. We don't want to go into that. But you see this particular curve and the values that we had obtained onto the y-axis, it is almost similar to this particular waveform which we had obtained from the Opamp, that is AD8030. Okay, getting my point? Okay, so that means what? That means we are able to obtain a logarithmic curve, or we are able to simulate this particular circuit with the help of Opamp, although that particular Opamp is not LM741, but that is also fine. So with this, what we can conclude is that your Opamp AD8030, it is highly stable. Let me just write over here. This particular Opamp, it is highly stable. This particular Opamp, it is highly stable. It is highly stable. Okay, and when you try to compare this particular Opamp, that is AD8030, I had also attached the screenshot of the waveform. If you want, you can just go through it. You see it is an exact logarithmic curve. Let me just highlight it for you all guys. See, if this is my input waveform, this is my, let me use this particular line which is available over here. Now if this is my input waveform, okay, this is my V in. Let me just highlight it for you all guys. V in. Okay, so this is my output waveform, something like this. Yeah, so this is my V out. Okay, so this is my V out, and this was my V in. This was my V in. Okay, great. So this particular Opamp, it is highly stable, that is AD8030. On top of that, if you try to compare this particular Opamp with the another Opamp, that is OP07, it is less stable. Okay, this particular Opamp, it is less stable as compared to AD8030. So let me just highlight this particular Opamp and let me just write over here that this particular Opamp, it is less stable as compared to AD8030. Okay, now if you try to compare this particular Opamp with LM741, that is this particular Opamp, so this particular Opamp, it is least stable as compared to LM741, sorry, not LM741, my bad, as compared to AD8030, AD8030 and OP0. I'll write over here 0 as this so that you shouldn't get confused over here, as compared to AD8030 and OP07. I hope that you understood this particular point. Okay, great. So now when I say that this particular Opamp, that is AD8030, it is highly stable, so what does that mean? So now let me add one more slide over here. Okay, don't worry, I'll just provide this particular PDF into the resources section, so that it will, like, whenever you will be referring my PDF, it will be very easy for you to understand this particular concept in the easiest way. Okay, so now let me just write over here that when I say that this particular Opamp, that is AD8030. Okay, so this particular Opamp, that is AD8030. So when I say that this particular Opamp, it is highly stable, right? It is highly stable. So what does that means? When I say that this particular Opamp, it is highly stable as compared to other two Opamp, as compared to other two Opamps, So what does that means? That means, let me just write over here, that means the characteristic of this particular Opamp, so that is AD8030. So the characteristic of this particular Opamp is almost equivalent to, or it matches somewhat to the ideal op-amp. That is this ideal op-amp characteristic. What does that mean? That means we all know that the ideal op-amp should have infinite gain. Okay, it should have infinite bandwidth, it should have very less noise and all, whatever that is, we all know that, right? It should have high input impedance, low output impedance and all, which we had already discussed upon that. So this particular property, you know, is almost equivalent to AD8030, although the input impedance, the gain, the bandwidth of AD8030, you know, it won't be infinite, but it will be very much high as compared to these two op-amps. Okay, that is LM741 and OP07, and that's why, since its characteristic matches with an ideal op-amp, that's why if you look over here, it is able to give this kind of logarithmic curve. Okay, so that was all about logarithmic amplifier. I believe that you understood this particular concept in depth. Yeah, and there is one more point to explain that, but before that, let me just highlight this particular point so that whenever you will refer this particular PDF, it will be easy for you to understand this particular concepts properly. Okay, yeah, there is one more point to discuss over here, and that is this, that is the log amplifier does not perform so well for large input signal. So for small input signal. So if my, let's suppose input signal, if my input signal is, let's suppose 1 millivolts or maybe 2 millivolts or 10 millivolts, whatever that is, so I won't get a desired output. So output is not desired as desired. Okay, so remember this particular point very carefully. I'm just writing this particular point over here. Log amplifier performs well only for large signal, large input signal. I mean to say large input signal. And when I say that I'm giving large input signal, that doesn't mean that I'm giving 100 volts, 1000 volts. No, I'm just talking about 1 volt or maybe 3 volts, something like this. So this kind of signal, maybe up till 5 volts. Okay, and it fails. It means logarithmic amplifier fails for small signals. Okay, because if you look very clearly, if I try to see that that is log of 1, which is 0, right? And if you try to calculate a log of maybe 0.01, so this particular value will be negative, right? So basically we won't be able to obtain a proper graph or a proper curve at the output side. Okay, because since the input signal is very small, so the output will be very less. It will be in negatives, right? Okay, so that is the reason for that. And I would also like to give you one more point, that is about the anti-log amplifier. Although we had not covered anti-log amplifier in this video, no worries, I will be uploading that particular video as well. So anti-log amplifier is exactly opposite of this. So it performs well for small signal, only for small input signal. Okay, only for small input signals. Okay, and it fails for large input or large signal. I'll just write over here large input signal. Okay, I hope that you are able to understand this particular point. Don't worry, I'll explain this particular point in the anti-log amplifier when we will focus upon that. Okay, now let me just show it to you that how exactly it fails. So yeah, this is AD8030. Now instead of 5 volts, what I'll give, I'll just provide a voltage as maybe 1 millivolts, or maybe, yeah, it's fine, 1 millivolts, and let's see what kind of output we are getting. So now let me just run this particular circuit, and you see we are not getting a proper logarithmic curve which we were expecting at the output side. This is because our input signal, it is very small, that is 1 millivolts. Okay, now let me, instead of 1 millivolt, let me put maybe 3 volts. Let's see what happens. Let me run it, and you see we are able to obtain a logarithmic curve, right? Instead of 3, maybe if I'm putting again, let's suppose maybe 5 millivolts, let's see what kind of curve we get. You see it is not giving a proper logarithmic curve, right? And you see the value is in negative, it is very less. Okay, on top of that, if you put very very large voltage, that is 5 volts. Okay, for 5 volts as well, at the output side we will get a negative voltage only. Okay, but we are able to obtain a proper logarithmic curve. Okay, so this was all about a logarithmic amplifier, and I believe that you understood this particular concept in depth. Okay, so this particular concept is not explained. Okay, the concept of logarithmic amplifier using an Opamp, this particular concept, it is not explained anywhere on YouTube or maybe on any other social media platform. Okay, so if you watch this particular video entirely, and if you enjoyed this particular video, if you like this particular content, this kind of content which I had presented in front of you, so it's my request to you all guys that you please make sure to like, share and subscribe to my YouTube channel. Okay, also make sure to share this particular video with your friends or maybe with your engineering friends. Okay, or those friends who like to design these lots of circuits and all, play with circuits and all. Okay, so what I'll do, I'll just end this particular video over here, and make sure to refer the description box. I had put in the link of my courses as well, and I had also put in the link of this particular website as well. Okay, so make sure to read this entire information which is provided over here, and then try to plot this particular waveform onto the LTspice software on your own. Okay, great. So I really hope that you understood the concepts that we had discussed in this particular video. But still, if you have any doubts, if you are facing any difficulties anywhere, it's my request to you all guys that you please make sure to ask those particular doubts into the communication section or into the comment section, those who are watching this particular video onto the YouTube channel. Okay, so I'm ending this video over here, and in the next video we'll see some new concept that is maybe about anti-logarithmic amplifier. Okay, thank you.